Hello, in this video we're going to talk about quantitative applications of Le Chatelier's principle. So up until now we've done this qualitatively, which way is equilibrium going to shift, if this or that is done to the system. So now let's put numbers on it. And so I'm going to talk about this by way of giving you an example. So here's an example. We have some equilibrium, PCl3 plus chlorine gas goes to PCl5, and you're given the equilibrium constant. And then for this particular problem, you're given the partial pressures of each species at equilibrium. That's nice. You could imagine we could make a two-step problem where the first step is calculate these numbers that are on the bottom right now. And then the second step is what happens when you mess with equilibrium. But we're not doing that here. Here it's just given what are the equilibrium pressures. Now here's the perturbation. So we inject chlorine gas into the mixture, and now the total pressure jumps to 263 torr. So given this perturbation, calculate the partial pressures of all species after equilibrium is re-established. So you can imagine it this way. You have equilibrium, you poke it, or prod it, or inject chlorine gas, and it's going to resettle back to a different equilibrium, but still equilibrium, right? So the partial pressures will be different, but it will still be at equilibrium. So now the first thing for this particular problem we have to do is figure out how much chlorine gas we actually injected. And this is, I guess, specific to the problem here, right? You could say we put in this much chlorine gas and you don't have to do this step. But that's not given here, so we want to figure out how much chlorine gas is injected. So we have this total pressure at equilibrium when we start, just the sum of all the partial pressures. And now, well, here's the new total pressure is 263 torr, and that is increased from the original total pressure by the amount of chlorine that you added. So if you just do some subtraction here, 263 minus 243, it tells you that 20 torr of chlorine gas was injected into this sample. Okay, so now we can use that and use an icebox. So our initial values here are the partial pressures that we're starting with, which in this case happens to be, it was at equilibrium, then we added 20 torr to the chlorine gas. Okay, so now these are initial pressures because we're not at equilibrium. Now the change, well, from your qualitative understanding of Le Chatelier's principle, you know that if you add a reagent, you're going to push the reaction to the right to make more products. And so this change is going to go towards the right. So we're taking away PCl3 and chlorine gas, and we're making PCl5. And then the equilibrium line here is just the sum of the first two lines. All right, so now what we do normally is we take the form of the equilibrium constant, which is written here, and then we plug these numbers into it. We know what the equilibrium constant is. We know that at equilibrium, our partial pressure of PCl5 is 217 plus x, whatever x is. We're going to have to find that. And then in the denominator, we have the pressures of the reactants minus x, because it's going to reduce the overall pressure as this reaction shifts to the right. So now we just need to find x. Simple in concept. In this instance, going to be another quadratic formula we have to use, so a little more algebra. And so walk you through the steps. So the first thing I always do is FOIL the denominator here. Take the first, the outside, the inside, and the last, and multiply them together, and get this. And then I'm going to take this whole denominator and multiply it to both sides. So that means it goes away on the right. Then on the left, it's multiplied by 1.25 torr. So then if you distribute 1.25 into all three of these terms, then you get the following on the left side. Then we collect the terms and say, okay, 1.25x squared, then we have x, we have the term without x equals to 0. Okay, so now we can use the quadratic formula. Here's a, b, and c. So you plug that into the quadratic formula, and then you get these two answers. Now for this problem, we can't immediately throw one of them away as incorrect, and so because there's not one that's negative, and so we'll have to figure out what to do here. All right, going back to the original icebox, now we can figure out which one of these roots makes sense. If you take 13.2 torr and subtract 101.7 from it, you're going to get a negative number, and that doesn't make any sense. You can't have negative pressure or negative concentration. So the 101.7 root is invalid, and we'll use the 6.52. So now you could either just take the 6.52 and plug it into x and then solve that way, because the goal is to solve for the equilibrium pressures of everything. Or you can do that same thing in an icebox. So we're going to do a second icebox. Here's the initials. Now we know what x is. So basically we're taking the first icebox and plugging in our number for x. And then now we can do the math for the equilibrium line, and we get our pressures at equilibrium. So now we have solved the problem. We know the equilibrium pressures after this extra chlorine gas is added, and it turns out to be a little more product than before and less reactants than before. All right, so now one thing you should always do is double check. So here's the reaction in the Kp. Let's plug in these equilibrium pressures into the form of Kp, and then, oh great, it equals what we started with to the number of sig figs we have. Awesome. So we know that this worked. So basically, you already know how to do this kind of problem from the previous videos and stuff that you've watched. It's just figuring out from the context of the problem that the initial line is where it was before equilibrium plus whatever perturbation you had, and that's our new initial. And then you just do, an equilibrium problem with an icebox like you have before, and it's not a problem at all. So just remember, this is a little tweak for how the setup goes and the start of the problem, but then you do know how to solve it. All right, and with that, thanks for watching.